Good morning. It was a tough week, but we finally here, doing our usual stuff. Learning how to compile programs. Oops. This one. Oh, I have new messages. Papa. Okay, let's get to our today topic. CS6120. By the way, since the last stream, I did a quite impressive work, not on the compiler itself, but on the environment where our compiler related code is running. And here in packages directory you can see a lot of new stuff and packages model, I mean. We can find this commit, this one. What we basically did here, instead of using package for channels which uses channel build system, which is unbelievably slow and like requires hours, minutes to start the REPL, we made our own package definition with usual Guile build system, which takes list of channels, generates git checkout for channels records, and combines those git checkouts into one directory. And also it respects I don't remember which file, gixchannel file content, and it looks up for source code directories defined in gixchannel and obtains this source code and put everything in one dir and after that it just builds all those source code like this. Unfortunately, it's not 100% universal, because you can specify some native dependencies for channels, which may be problematic if your channel depend on, I don't know, libJSON, or maybe something else, maybe some even more native dependency, some binary. This won't be reflected here. However, probably it won't be reflected in and it won't work in channel build system as well. So what we achieved by this, we achieved the following property. Now I can start an REPL server in just like few seconds, and if I restart it, it should take even less time. Nice, it's manageable, like 1-2 seconds, and the slowest part here is git checkout. Yes, it takes time to do what is happening here under the hood. I don't know why it takes time when our channel is already in the store. I can have some guesses why it happens, but I won't do it. And we can of course optimize it, but 1-2 seconds and it's under the load when I'm streaming is not like that huge of a problem. I can like handle it and wait this time. Few minutes is not acceptable and like very frustrating. Few seconds is okay, manageable. We can of course optimize it, but it doesn't make sense because we will spend much more time optimizing it rather than getting benefits. Okay, that means we could jump to this file and start evaluating stuff and all the things. Two more auxiliary things that I would like to do. First one is actually understand why the pipes and all related stuff hangs evaluation thread and I can't interrupt it. Maybe I would even wrote a test for Guile Areas and like do all that stuff. But I wouldn't say I'm lazy, but this thing doesn't feel very rewarding. You spend like hours and hours trying to understand how to fix this thing, and even if it's technically possible to solve this problem, you just don't get anything. You don't get anything visible. This is why it's not very rewarding, and it's hard to force you to work on this thing. And the second thing that I would like to work, not I would like, but would be good to work, is to create a library with more convenient wrappers for working with external processes, because right now the stuff that is provided is not very usable, like open output pipe, open input pipe, open output input pipe, and pipeline functions should do like something useful, but they're not very useful because they are providing deadlocks when I use both input and output ports to interact with them, which is not very convenient, and we need a better API that we don't have. And the library for interacting with external processes would be good. But not today. Today we will try to catch up with the course. We actually almost already on schedule with our schedule. Schedule is here. Lesson 4, data flow. Oh, we are not on a schedule. February 13 should be lesson 5. Okay, we are one lesson behind the schedule, which is not very cool. But not that bad. We started much later, and we catching up. We will do it in a couple more lessons, I guess. Okay, let's go to lesson 4. We have 2 videos here. Quick task notes. The data flow framework. Yeah, the reason I would like to have this API ready for me, because I want to use the stuff that we packaged with gigs like Bril, Dana, and other binaries directly in my scheme code, like just writing tests and the stuff that I would like to check. I want to execute all those things directly from the REPL. That means that we have one more task for internship, for possible internship for Arei. Sunday, Saturday, Friday. What I would like to do, I would like to add IS9 external process idea to RT internships. Okay, and I will do it after the stream, I guess. So for now, let's focus on compilers. Probably we won't be doing much coding today. We will just focus on the lection, and we'll try to understand it deeply. Maybe we'll experiment with some code snippets, but I don't think we will do much coding. Anyway, let's start our timer that will allow us to keep track of breaks, so we don't forget to stand up and to rest and eat and all those things.
This lesson is going to be about global analysis. We're going to see a general technique for doing global analysis that's based on lots of local analyses. The technique is called data flow. data flow is a kind of a generic framework that you can fit lots of different analyses into, and then using a single common algorithm, turn that into global analyses that can deal with arbitrary control flow graphs. First, I want to start out by getting you used to the idea of what a global analysis looks like, one that is actually sensitive to control flow. So let's look at this program. This is a really simple program. I've sort of transcribed it here in purple to make it slightly more readable with an if-else statement. Now imagine that your task is to do some sort of constant propagation on this program. That is, we want to know what A and C might be, that is like what constants they might be, when we're printing them out at the end, when we finally print out their difference. So the question is it possible to replace A with a constant, or is it possible to replace C with a constant? And the point about asking this question is that it is a global property. You can't answer it by just looking at the basic block at the end. You kind of have to look at the entire control flow graph to decide which times you define, that is, which times you assign to A and B, which of those are actually still relevant at the time that you print something involving A and C. To answer questions like that, we will have to look at the entire control flow graph. That is, we'll have to think of things in terms of basic blocks and the way they're interconnected. And to make it entirely obvious, I really want to emphasize that this is not something that can be solved using the same sort of constant propagation LDN techniques that we saw in the last lesson in general for arbitrary control flow graphs. It may be possible to do that for this particular program, but one simple way to break that kind of reasoning, that is just sort of scanning down the list of instructions and updating things one by one, is to realize that this program is equivalent to one where we take this end block and say we add an explicit return to it and then insert it way up here. And then if we do something that just is sensitive to the ordering of instructions, then this will clearly be wrong for the actual CFG. This program is equivalent. Just moving basic blocks around doesn't actually affect the semantics of the program, but just reasoning about things in the order of instructions will be completely wrong if we put this block in the wrong place. And of course, in general, we need to write global analyses that can deal with any arbitrary control flow graph. That is, really imagine any arbitrary topology where the vertices contain any code whatsoever, and they can be connected in any control flow structure that you can imagine, any arbitrary edges. We're going to have to deal with that structure. And that's what data flow is going to give us a kind of a generic framework for reasoning about. Before we jump into the framework, I want to pose one particular global analysis and make it a little bit more formal so we can see how to set it up as a data flow problem. The problem we're going to solve is determining reaching definitions. I've written the formal definition of what a reaching definition is up here on the slide, but it's going to take a few sort of sub-definitions in order to get exactly what I mean. Roughly speaking, I mean, we want to know for every instruction in the program, we want to know what other instructions that wrote to variables are still valid at that point, that is, are still the most recent assignment to that variable. To define it, however, take a look at these four definitions of funky compilers terms that we will build up here. The first is a use. An instruction is a use for all of its arguments. So if you say like print A, for example, that's a use of the variable A. Conversely, a definition is just an instruction that writes to some variable. That we call that a value instruction in Brill in particular. So any instruction that writes to a variable, you can also call that a definition of that variable. An available definition is one that reaches a given program point. So by reaching, I just mean that it is still the most recent definition of that thing. And finally, we'll use the terminology kill. Sorry, but this is just the terminology to say that any definition kills all the currently available definitions for the same variable. That is, anything that overwrites a variable kills all the previous definitions at that point. So to return to our definition of reaching, this is just to say that if you have a definition of some variable v, that reaches some other instruction. Remember, the definition is an instruction. That reaches some other instruction, call it u. If there exists a path in the CFG from d to u, that is, like, it's possible for control to go from the definition to the use, where along that path, and you sort of trace all the basic blocks from one path to another, there are no other assignments to that variable v. That is, that definition is not killed along the path. So the reaching definitions problem, that is the analysis problem we want to solve, can be put this way. For every definition and every use, and remember, definitions and uses in Brill terminology are instructions. So for every instruction that either uses a variable or writes to a variable, we want to determine whether that definition reaches that use. If you like, you can think of this as a big matrix where you write all the instructions along the x-axis and all the instructions along the y-axis. And we want to put in a 1 or a 0 at every location to say if this definition reaches this use. So that's the formal definition of the reaching definitions problem. I want you to solve this analysis by hand for the example that we've seen so far. The way this is going to look is that you'll need to, for every, like, you can come up with names for every definition. So let's call this A1 because it's the first definition of A, and this is A2, and this is B1. You can come up with names for every single definition, and then look through at all of the uses. That is, every instruction that uses variables. There's only one use here in the entire program, which, actually, sorry, there are two uses. There are these two uses in the final block, in the end block here. Decide which definitions, according to your naming scheme, are reaching this point and reaching this point. Go ahead and stare at this control flow graph for a while, label all the definitions, and make a list of the definitions that reach those two uses.
Okay. For variable a, we have two definitions, a1, a2. A1. I'm curious what cont is, where it's defined. But probably if you don't see the definition of cont, we can consider it like to be arbitrary value, then it means first definition can reach the usage here, and the second definition also can reach the usage here. So both A1 and A2 reaches use, I don't know, use 1 of A, use A1, okay? For variable B, B1, B2, B1, B2 both can reach B usage 1. We don't have B usage, we don't need it. Okay, what else we have? We have D and C. Both C also can reach this usage, and there is no definition for D, so it's okay. So the matrix for every variable will be basically 1, 1, 1, 1 for A and C and corresponding usage here.
This was a little bit of a trick question because I forgot that there was another use in this program. There's a third use. Of course, this branch instruction reads from the cond variable. The cond variable is an argument to the function, so we'll also want to incorporate that variable as another definition. That's not an instruction, it's a definition that comes from the argument. So we'll want to consider that variable, just like any instruction that defines a variable, as a definition when we're asking which definitions reach each use. And we'll also, of course, want to write down the uses for that third use. My answer for which definitions are available, or reaching, rather, at the branch instruction here are that, of course, cond1 is, and A1 and B1. Those definitions reach that point.
Okay, trying to understand. He wants to take arbitrary points and for them list all the definitions available at this point.
Traversing through the rest of the graph, we now need to answer that question for this assignment to D, which is both, of course, a definition and a use. As I've labeled it as D1 because it's a definition, but as a use, we can ask which definitions reach there, and the answer is pretty much all of them. That is, cond1 reaches there, so does A1 and B1 and A2 and B2 and C1 and C2. All those definitions reach this point. And, of course, for the final point, the set of definitions that reach there are exactly the same.
This reminds me the lexical scoping.
With the addition of D1. Great, so you solved a global analysis problem. So how did you solve this? You used your human brain looking at the program and looking at all the paths through the CFG. That is, presumably, you noticed that A1 reaches this point because this definition has a path along which A is not killed that reaches this point. And you notice that B has a different path along which it is not killed and therefore it reaches that point. So you kind of had to look at every single definition and try looking for paths through the graph. That was tractable for the small CFG, but you can see how it will quickly get unwieldy and might even be pretty confusing if we end up having cycles in the graph. That is, if we have loops in the control flow. To handle general graphs and to do this for arbitrary problems, not just reaching definitions, we have the data flow framework. The data flow framework is kind of a recipe. That is, you feed it a few ingredients. That is, like, you think about your problem that you want to solve as a global analysis. You feed it some information about that problem, and then you ask a data flow solver, that is an off-the-shelf algorithm for solving arbitrary data flow problems, to give you back a solution. So the general idea boils down to these 4 steps. The first step, the first ingredient to solving a data flow problem, is to figure out the thing you want to know at every point in the program. But instead of saying that we'll calculate it at every single instruction, in the data flow setup, we will just try to calculate that thing at the beginning and the ending of every basic block. That is right before the first instruction in every block and right after the last instruction. So we need to figure out like what information is we're trying to calculate at those points. For the reaching definitions problem, for example, that's like the set of definitions that reach there. So that's like the quantity we want to calculate for those program points. The next step is to write an equation for every single block that relates the state at the beginning to the state at the end. That is, we will do a local analysis on every block. This is kind of the awesome thing about data flow analysis, is that in this step, you get to reason completely locally. You can pretend that this is the only block that exists in the entire world and ask questions, for example, about how, assuming that we know that some definitions reach the beginning of the block, what definitions must therefore reach the end of the block. And you can temporarily forget about the entire structure of the CFG and just think locally about the one block. Then the rest of the CFG comes in the next step in the recipe, which is to add inequalities that set up equations according.
This is a very cool property about blocks, because we don't have any control flow control operations inside one block, so you can jump from the middle of the block to some other location. We can know for sure what is reachable at the beginning and what is reachable at the end, and what is overridden. Yeah, I guess it's the right word. Pretty cool. I am very glad that people invented this separation of the control flow graph into the blocks. I mean, invented the idea of control flow graph in general, I guess. Very convenient.
To the edges. That is, for example, that somehow the quantity at the end of this basic block must be related to the quantity at the beginning of a basic block that it jumps to. Finally, we will take those systems of equations, that system of equations that we have just made, that is a bunch of equations that relate the beginning to the ending of each basic block, and a bunch of equalities that capture the edges in the control flow graph. Those make up a bunch of equalities, and we will hand that over the wall to an off-the-shelf solver that will tell us the answer, that is the value at every basic block entry and exit. The magic thing about data flow analyses is that you don't have to invent that solving algorithm from scratch every time. I'm going to show you the pseudocode for a solver for generic data flow problems in just a little bit, but you don't have to make a new solver every single time. You can use a generic solving algorithm for data flow analyses and just provide it with these ingredients to make it do wildly different things each time. So to make this concrete,
we want to know the entry index of a block. Okay, let's see the examples, and maybe it will become a bit clearer.
This equation solving view says that we want to introduce sort of variables that we can write equalities on. So let's say that there's an in and out variable for every single basic block. That is like the sort of incoming information and the outgoing information for every block. These will be distinct variables. So I'll label this as in for B1 and out for B1, and similarly for every other basic block. The function I mentioned before, that sort of local analysis function for every block, that's sometimes called the transfer function for what it's worth, will relate the in for every block, that is, for example, for B1, to the out for that block. So we'll get a bunch of equalities that way. We will also want to relate the blocks to each other. That is like the exit of one block to the entry of another one. So here's my question for you. I want to know what to write for this equation in order to capture the edges in the graph. That is, what should I make the variable in left, that is the value for like some arbitrary value, if we can imagine as like sets of reaching definitions, but anything we want to ask about, like what is true about the program at the entry to the left block, what should that be equal to in order to capture the structure of the CFG?
Let's go back a bit.
Want to relate that block. Analysis function for every block, that's sometimes called the transfer function for what it's worth. Sort of the function I mentioned before, that sort of local analysis function for every block, that's sometimes called the transfer function for what it's worth, will relate the in for every block, that is, for example, for B1, to the out for that block.
Okay, I got a bit distracted and missed this part.
So we'll get a bunch of equalities that way. We will also want to relate the blocks to each other. That is like the exit of one block to the entry of another one. So here's my question for you. I want to know what to write for this equation in order to capture the edges in the graph. That is, what should I make the variable in left, that is the value for like some arbitrary value, if we can imagine as like sets of reaching definitions, but anything we want to ask about, like what is true about the program at the entry to the left block, what should that be equal to in order to capture the structure of the CFG?
Okay, the question is clear. In this information, in these variables or equations, we need to keep some kind of information that will help us to understand the structure of the control flow graph. And at this point, the only information we can write into is the block we are coming from. So for in left, it will be B1. For in right, it will be B1. For in end, it will be left and right. I guess it is what he's asking for.
Should that be equal to in order to capture the structure of the CFG? I think it should be
Yeah, I don't have any other good assumption here. I thought that we can store some additional information, probably some outgoing edges, but probably no, because we will generate out left based on the last instruction of the block.
equal to out B1. That is, whatever was true about the program at the very end of B1 has definitely
One more time.
out B1. That is, whatever was true about the program at the very end of B1 has definitely better also be true at the beginning of the left basic block. That's also true of the right basic block. That is, that should also be equal to in right should be equal to out B1. Whatever was true about the program that we're wondering about.
Okay. I got it. So we kind of propagating some information from the previous block to the next one. So for the in end, it should be a combination of out left and out right. So it should be some merge function which takes the information from a few blocks and put it into in end.
At the end of B1 should totally still be true at the beginning of the block that it jumps to. So here's a somewhat harder question. What should the value for in end be? That is, what should I set up as the equation that gives the value, that is like what is true about the program at in end? That's
we already answered this question. It should be some special function which combines value from all other blocks, and for this particular example it will be this function, for example, call it merge of out left and out right.
A little bit trickier. There's going to need to be some sort of way of combining whatever was true at the end of the left and right basic blocks. That is, we can't say that this is, well, whatever is true here is exactly the same as out left. That is like the end of the previous of the left basic block. It has to be that we need some way of combining those pieces of information. So it's definitely going to be related to out left. That is, in-end will have something to do with the out left and out right variables. But this sort of points to one last ingredient that I didn't show you in the recipe, which is we're going to need some way to merge that information. That is, this is sort of the last piece of the puzzle. In order to capture sort of direct transfers of control, we can just set things equal to each other. But when a block has more than one predecessor, we're going to need a way to sort of figure out how to mash together the information from both sides. So here's kind of a fillable form that I want to fill out for reaching definitions, but you can fill out in a myriad different ways in order to make different global data flow analyses. The first thing you need is an initial value. You need a value for the thing you're trying to compute to sort of kick off the whole thing, to provide sort of a seed for the system of equations. We need a value for the reaching definitions, say, at the very beginning of the first block, the entry block of the entire function.
It will be just cont, I guess.
We've decided that our representation for the values you want to compute are sets of definitions, so this should be a set of definitions. The next thing we need is the transfer function. That is, we need a way to compute the output value, the output set of definitions, given the input set of definitions for every single block. And finally, the last thing we need is a merge function. That is, we need a way for whenever you have a block with multiple predecessors that has, it looks in the control flow graph, something like this, we need a way of taking the output values from the predecessor blocks, taking those together, gathering them up, mashing them together somehow, and computing the output value, the input value for this basic block. That is, for reaching definitions, these of course are all going to be sets of definitions, and we need a way to compute the set of reaching definitions at the entry to a basic block, given that we know the sets of reaching definitions at the end of all the predecessor blocks. So once you do this, that is, once you fill in this form for a given data flow analysis, you're basically done, and we can, in just a moment, see how to solve that system.
Okay, the initial set will be just containing only one value. The transfer function, or how it was called, will be I can imagine like imperative definition, like we go through all the instructions and we find all the assignments operation. And if we see assignment operation, we check if our set of definitions already contains this variable, and if it contains, we remove this definition and substitutes it with new one, and if not, we just add this definition. So basically we go through the operations, we see assignment operation, we check if our set contains this variable, definition for this variable. If so, we remove, and after that we unconditionally adds a new definition for this variable. That's the transfer function. And merge function will be the merge function will be just merging all the sets. It's basically set merge operation. That's it.
I want you to pause the video now and try filling in these blanks. Come up with an initial value, a transfer function, and a merge function for reaching definitions. Here are my answers. For the entry to the basic block, we will want to use a set representing the arguments to the function. That is, just like we saw for the cond variable in our little example above, we want to sort of seed the system with the set of definitions that have reached the very top of the very first basic block. So that's the set of arguments. Next, we need a transfer function. Because the value we're computing here is a set of definitions, this function is going to look like a operation on sets. That is, this thing is a set, and this thing, the thing we're computing, is a set. And it's also going to have to like ask some questions about the block. So my answer is going to be an equation involving this set in B. Okay, my answer is that if you take the set of definitions that were available at the very beginning of the block, and you then
let's come up with a bit more elegant solution. Can we pre-compute something about the current block? Yeah, we can understand the set of definition provided by this block, and we can merge the in B and this set of definitions for the current block, but it will be basically the same thing, just without implementation details, without so much implementation details I mentioned earlier. So yeah, I probably don't see like much more elegant solution here. So we will stick with our previous idea.
Remove, this is like a set difference operation, a symmetric difference operation, and you take out everything that was killed by that basic block. Then we're almost there. Those things that were reaching this block, but then were killed somewhere in the block, those are no longer reaching the end of the basic block. But some new things are reaching the end of the basic block, which are the definitions of this block. So if we take the union of the definitions of this block and the symmetric difference between the things that were defined at the beginning and the things that were killed by this block, that should be the reaching definitions at the
Yes, that's very true.
the end of the block. It's really common for the values that we're computing in data flow analysis to be sets, and therefore it's really common for transfer functions to look like a bunch of operations on sets. That is to take the input set and take local analyses about the blocks that compute sets, and then do SETI operations on them like union.
The cool thing here is that it is a bit more high level way to represent this transfer function, which I like. So we can take our inb, go through the block, find all the things, all the definitions that will be killed by this block. We first remove it from inb, and after that we can go through the block one more time and find all the definitions which will appear in this block, and after we just merge those two sets. Looks a little bit more elegant, but basically it is the same thing that we discussed earlier, just not that detailed and imperative, more high level.
Symmetric difference and stuff to compute the value for the output. Okay, so finally we need a merge function. That is, we need to say, okay, given that I have a basic block, I want to know how to compute the reaching definitions at the top, given that I have a bunch of sets of reaching definitions for my predecessors, the ends of my predecessors. The merge function for reaching definitions is just union. And I'm writing it really big because it's like a big union over all the predecessors, all the end variables for the predecessors to this block. If we have that, that is a complete definition of the reaching definitions problem. And all we need to do is solve this problem. So the next step is going to be looking at a generic algorithm for solving data flow analyses, given these ingredients that we've just given for reaching definitions.
Okay, let's do a small break. Hello, David. Hello, David. When the cont splits into the two blocks, do the C definition count as two separate definitions? Let me see. Let me see the program example. Yes, of course. We have two separate definitions for the C. What is more important, even if those definitions will be the same, like C equal to const 5 and C equal to const 5, it will be two separate definitions, unless we perform any kind of optimization of control flow graph. I need somehow to make the timer visible, so I can, make people aware that I won't be here for a while. An interesting problem for that one. There is a formula for C that doesn't change, but it can be optimized. C equal 5 times E, where E is a predicate for the definition in the left and right cont. So you mean this is the way how we can optimize the definition of C, like move this definition from 2 blocks into 1 block and make it a different operation that depends on what block we visited. I guess it can work. But probably we won't see like such optimization in the real world. Yes, but in fact it doesn't simplify anything. Probably true. Okay, give me a minute. I will take a carrot or something and we'll come back. I'm just in time. So I have a banana instead of carrot, but it should be good enough. Let's start watching the lecture further.
And B1, those definitions reach that point. Traversing through the rest of the graph, we now need to answer that question for this assignment to D, which is both, of course, a definition and a use. As I've labeled it as D1 because it's a definition, but as a use, we can ask which definitions reach there. And the answer given these is the thing that I think the class ingredients that we've just given for reaching definitions. This is the classic work list algorithm for solving data flow problems. One thing that I think is remarkable about this algorithm is that it's so short and it's so easy to understand. It's remarkable that it works at all and that it works for any arbitrary data flow problem that satisfies some constraints. I think it's truly remarkable. So as I showed above, there's a few things you need to provide to this algorithm. You need to provide initial value and functions that we'll here call merge and transfer. The way the algorithm works is it first needs to initialize things. Here I'm sort of representing those in and out variables as maps. That is, like for every basic block, including the entry block, we will have an in variable, and the work list represents the blocks that still need to be processed. That is, that have preliminary values for their input and output variables, but still need updating. And eventually, this is going to start out as all the blocks because we haven't really analyzed anything. And eventually, the thing will terminate when we have no more blocks to process. So the way that the classic work list algorithm works is that you can pick any block at all from the work list. It doesn't actually matter what the order is. This is another remarkable property of this algorithm, that it remains stable, that is, the solving remains stable, regardless of the order that you pick. You can just take any arbitrary block that hasn't been finished. And what you do is that you update its in and out variables. You update its in variables by running the merge function. So you get the out variable for every predecessor. And to remind you what a predecessor looks like, we're in a control flow graph. This is us, the basic block in question. Call that B. And then everything up here is a predecessor, and everything down here is a successor of B. So if we take the out variable for every predecessor, and we call the merge function on it for reaching definitions, again, that's like the big union operator, that gives us the in value for this block. Then, now that we have an input value, we can just call the transfer function to do the local analysis on this block.
Okay, it's quite cool. It's actually quite cool. We have a list of blocks we want to touch, and if after touching this block we updated the output of this block, we add it into queue. Not the block itself, but all the successors of the block. So if outgoing values of the block are changed, we add to the queue all the values depending on this block. So we basically notify all the dependent blocks, like all the successors, that they need to recompute their values. And unless it stop changes, like the block in the queue stop changes, we keep like adding the successors of the block, and this network will be like network of those blocks will be updating until everything is stable, every value is propagated. It's very similar to propagator network. Very cool. Very unexpected to see this thing here. I'm curious what happens with cycles. Do cycles introduce new definition, or if the definition stays the same? This is an interesting question. And how like many cycles we need to go through. Yeah, we need to be very careful with cycles with this algorithm, because it, can get into infinite loop.
And compute the out block. Then finally, all we need to do is maintain the work list. And this just says that if we change anything about out B, that is, if that update set a new value for out B that wasn't the old value of out B, we just have to tell the algorithm that we now need to pay attention to the successors again. That is, those successors are going to have to look at our output value to compute their input value again. So every step in this algorithm is easy to understand. That is, that we need to sort of merge our inputs, do our transfer, and then ask for our successors to run. What I think is surprising, that is true, that you can prove about this, is that, like, given a few constraints, that this is guaranteed to converge. That is, it runs in a finite amount of time and gives you the correct answer. That is, it gives you values for in and out that satisfy the system of equations defined by your data flow problem.
The only like small thing that I don't understand so far, why we pick any block from work list. I understand that the order doesn't matter, but it would be a bit easier if our work list will be a list and we will be picking blocks consequently. Doesn't matter in which order they are placed to this list, but it will be like more determinate behavior, because like pick any block feels like we just pick a random block in this list and do something to it, which doesn't give us the termination predicate to become true. It doesn't give us a termination condition. Probably what is missing here in this pseudocode is the remove operation from the work list, because this while work list is not empty and only operation that adds to this work list. But probably pick operation kinda implies that we also take this block out of work list. So it's probably pop operation, not pick, but okay.
There's one extra detail about the worthless algorithm and about data flow problems in general that I haven't revealed yet, which is that there are two different flavors. There's forward algorithms and backward algorithms. The reaching definitions problem is a forward data flow analysis problem. And that means that it works by like having an initial value for the entry block and then traversing from predecessors to successors, that is passing information downward along the data flow graph. It's also possible to have backwards data flow analyses, where you have an initial value for the end of the exit block and you propagate information backward along the edges in the graph. This algorithm generalizes really nicely to backward problems. That is, all you have to do is kind of like flip the in and out direction, and you have to flip the predecessor.
Oops, I forgot to put the mic back. I hope you heard what I was talking about. Small recap. There is a condition for finishing the loop that work list is not empty, and there is no place where we explicitly remove the processed block from the work list. And I think that pick operation implies that we take the block out of work list, and it should be probably called pop to be a bit more explicit that it takes the block out of work list. That's it.
Successors and successors in this algorithm. And if you do that, you can do other analyses that we'll see in a little while that require a different kind of analysis where like information comes from the end and goes to the beginning. One last really surprising thing about solvers for data flow analysis. They work pretty much automatically if your program has cycles. That is, we have only really been considering examples where the CFG is kind of this feed-forward graph that doesn't have any loops in it. And I think it's remarkable that the algorithm still converges and still gives you the right answer, even if you have loops. And this is the really nice thing. If you had to reinvent analyses for loops every single time, you would quickly lose patience with compilers. So the data flow solver algorithms, like the worthless algorithm, provide a really nice way to deal with arbitrary graphs, including ones with cycles, like this one. If you calculate the reaching definitions for this program that has an actual loop in it, it will just work and will give you the answer that you expect. That is, it will satisfy the equalities in your systems of equations, which is super cool. I want to briefly touch on the requirements for what makes this work, because you can't just give like any arbitrary. You probably wouldn't want to like feed in a merge function, for example, that like flips a coin and then just decides whether to include reaching definitions or not. There are requirements in order to make the data flow analysis algorithm converge and give you the right answer. There's a really deep theory about what makes data flow analyses work, and I don't want to go off into the theory. You can read about that in the links for today's lesson if you're curious. But I do want to give you kind of an idea of what is a sufficient condition for a data flow analysis to be well formed, and therefore for the algorithm to successfully conclude things about it. The first is, and this is kind of the big one that you have to pay attention to, is monotonicity. That is, like in general, the values that you're computing, kind of through the solving of the worthless algorithm, they kind of have to only go in one direction for some definition of directions. That is, when we gather more information, and this is most concrete if you are computing sets, we have to be adding things to the sets. So you have to be able to define some sort of an order on the values you're computing, and you ensure that every time the worthless algorithm runs, things are only ever moving in that order. Maybe you can see how this in general ensures that the algorithm will eventually terminate. That is, that, like, if you have a order that it can eventually end in one way or another, then you by only moving in one direction, then you ensure convergence. That's kind of the proof of termination for this algorithm. So for example, you can imagine like the order for sets. It makes sense to use like the subset order. So if we are thinking about like sets of variables, as in this example, I'm showing a partial order that relates that's the subset relation on sets of A, B, and C. And the nice thing about this order is that it has a top element and a bottom element. That is, it has the empty set and then the set of all the finite set of all the variables that are being computed. Which means that if we only ever move one direction in this, and it doesn't matter which direction in this one, because there's a top element and a bottom element. If we only ever move one direction in this this relation, then we are guaranteed to eventually converge. That is, like someday we'll either, if we're going in the upward direction, we'll eventually get to the empty set, and then we'll know that the worthless algorithm will definitely terminate, or we'll eventually get saturated and get to the universe set, the finite set of all the variables in the program, for example, and then we'll also know that it terminates. So if it helps, if you want to like prove to yourself that your data flow analysis like fits this constraint, you can think of forming a partial of defining a partial order on the values that are being computed. So for example, if we're doing something with sets, then that partial order, you can use the superset relation, for instance. And you need to think of your merge function. You ensure that your merge function, whatever it is the meet, that is the greatest lower bound, on that partial order. So for example, for this partial order, the meet is the union operator. So in this sense, by like picking the partial order, you kind of fill out the entire recipe for doing data flow. The initial value has to be the top value, here the empty set, and then your transfer function has to be monotonic with respect to the order. By which I mean that if you have an ordering between x and y, then applying the transfer function to x and applying the transfer function to y should preserve that ordering. So x ordered with respect to y implies that f of x is ordered with respect to f of y. If you do that, then you have satisfied the requirements of data flow, and you're guaranteed to...
The web camera covers the stuff that he's writing, but it is probably the first time where I have like this definition of monotonous function used in my life. Like I had it in the first years of university and never met it before in my career, I guess. At least I don't remember where it was useful for me, and now finally the day came where it is used in the real world computer science, which is cool. The set theory I faced it multiple times, so I really recommend you to learn discrete math if you are in your early years of career and early years of university. This is just a really cool type of math, and I quite enjoyed it. I spent like one summer, a few weeks, like reading a book on a set theory, and this is quite cool. Can recommend it.
Get a correct answer, and for the algorithm to terminate and give you that correct answer. It can be useful to think about what even defines a correct solution to a data flow problem. That is, what is a correct answer for a system of data flow equations? The classic answer to this is to define it as the meet over all paths solution. So imagine this sort of idealized data flow graph. This is B1 we will think of as the entry block. So this is a path from the entry block to a given node that we're considering. That there are lots of possible paths potentially through other nodes not shown here from the entry block to the given block. We will say that a correct solution is if you sort of chain the transfer function across all the blocks along a path from the entry to your node, and then you take all of those chains and you take the meet, that is the merge function across all of those things, then you get the correct answer for the data flow analysis. So to write it out in symbols, we can say that like out for a given block, call it Bn, that is like the out variable for that thing, is the big meet, that is like take the merge function and apply it to all the paths from the entry block to Bn, and call that B1, remember that's the entry block, and then a bunch of stuff in the middle, and eventually Bn, and then take then we will compute the value going across a given path. So this will look like a bunch of applications of the transfer functions for all of the blocks, eventually applied to the top value for the partial order. So first we'll have to apply B1, and then we'll have to apply F for every block along the chain, and eventually Bn minus 1, and finally Bn, and applying the transfer function along the entire chain, and then taking the meet of that thing. That sort of defines the correct solution. Finding all the paths is of course going to be super slow, which is why we like the workless algorithm. And it's remarkable that algorithm, which is efficient, is guaranteed to find the same solution as this kind of like exhaustive look at all the paths thing. And just to be clear, it's not even clear how you would do it in a reasonable way in the presence of a graph with cycles. That is, like, if you think your naive algorithm is going to be like enumerate all the paths from the entry block to my block in question and then compute something for every single path, that ain't going to work if your graph has cycles, because enumerate all the paths will never finish. There are an infinite number of paths in a directed graph with cycles, of course. So the argument for the correctness of data flow algorithms, that is like for the workless algorithm for solving a data flow problem, relies on the properties of the partial order that's sort of underpinning your data flow problem. I'm not going to talk about like that exact proof, but if you're super curious, there are links that you can follow associated with this lesson. The final thing I want to do in this lesson.
The partial order means that between some of some elements of your what is English name for it? Like you have the set of all values available in your domain. Okay, let's call it domain. Here it will be empty set with one element A, B or C, AB, AC, BC and ABC. And partial order means that some elements of your domain have a relationship between them. For example, here we know that B is less than A and B, and B is less than BC, and the same for C is less than AC, but we can't compare B and AC, and we can't compare B and C. Like the set of one element are not like comparable if they are not the same. This is what is a partial order. The complete order, I hope it's the right English term for it, will mean that we will have a relationship, the order a relationship between each element. So in this graph it would mean that between all elements will be the edge, and it will be like a directed edge which shows the order. What else we have here?
Variables at different points, and then compute something for every single path that you can follow associated with this lesson. The final thing I want to do in this lesson is take this framework.
And monotonicity is already discussed. If x less than y, less in a general sense, not necessarily like a number. It can be in a way of partial order defined on sets. If x less than y, that means that f of x also less than f of y.
We've learned about, and instantiate it. Think about how to instantiate it for lots of different global analysis problems. So I've made a big table here that lists, and you can see these analyses in the notes for this lesson as well. It lists a bunch of global analyses that you can solve with a data flow analysis problem. And the idea is that you can do this by, you can solve all these problems just by filling out the cells in this table. That is, you just have to provide the ingredients, the domain that is like the types of things that you're calculating, the direction, forward or backward, the merge function, and the transfer function. I'm going to explain to you really briefly what all these things are, and then it's going to be your task now to think about how to fill in the cells of the table in order to come up with a setup for a data flow problem that solves, for a data flow analysis that solves this problem. We've already talked about reaching definitions, so I won't talk about that one. Live variables are the set of all the variables that have been written to and are going to be read or might be read sometime in the future. That is, it's not just the variables that are defined at a given point, it's the ones that are still necessary. You can see how this might be useful in eliminating some dead code. I'm taking your dead code elimination to kind of a data flowy place. Constant propagation is something that we did locally using LVM.
Okay, I understand the idea of analysis, but I didn't understand what those function means. Like the direction backward, what does it mean? So probably if you go to the final block where every block ends, I guess, and we define sets of variables and go backward, like to predecessors or what? It's open question for me at the moment.
But constant propagation on a data flow graph needs some way to understand, like at every point in the program, whether a variable is guaranteed to be a constant, and so you can replace that variable with a constant. Available expressions asks which expressions have been computed. some way to understand, like, at every point in the program, whether a variable is guaranteed to be a constant, and so you can replace that variable with a constant. Available expressions asks which expressions have been computed before, expressions in terms of variables. And this, of course, is useful in doing common subexpression elimination on an entire control flow graph. Then initialized variables I included. It's not about optimization. Initialized variables, you know, in Java, how it complains at you if you define a variable, if you say like string s, and then later on you try to say like s plus hello or something, it will complain about you at the point where you use a variable when it's not defined. This, of course, is a flow-sensitive property. It has to do with the control flow graph. For example, you can do all sorts of like loops and ifs and stuff, assigning to variables at different points, and that affects whether you should get an error when you try to read from a variable that's uninitialized. So the initialized variables data flow problem answers that sort of thing. Interval analysis is an interesting one. It's about numerical problems. So when you actually care about like the floating point or integer value of a variable, and it asks what is the interval that is, like, say, like from 5 to 42, for example, that is the range of values that variable can take on. For example, if you end up with this range and eventually you have like something that says like if x is less than 45, then you can simplify this to true, because you know that you don't know exactly what the variable is, but you do know that it's less than 45.
It's a nice coincidence that recently I was reading the dissertation on propagator networks, and there was examples with ranges which are probably very similar to interval analysis that is happening here. So next time I will be reading this dissertation, probably I get like this connection and understand deeply how it works, which is cool. Which is very, very funny.
All of these things can be solved with suitable definitions of the domain, the direction, the merge function, and the transfer function. I want you to pick just one of these analyses and think through how to fill in the columns. That is, like, maybe you want to take constant propagation. Think of I've given you kind of the domain that is like the thing that we're calculating. That's pretty easy. Think about whether you want to do that forward or backward, that is predecessor to successor, or the other way around, and come up with a merge function and a transfer function. Do that now, and then of course offline you're welcome to, in your implementation, play with as many of these things as you like by plugging them into a Dataflow framework.
What is written here? 6RT, ORT, evaluation. Okay, let's think on the constant propagation. Time to take a break. It's still not very clear to me how we calculate this characteristic for each block for constant propagation. What if In the in block, we got information about all the constant values of predecessors for this particular variable, and if they have the same value, we just merge them. I think it should be forward. The same as with reaching definitions. And probably it should be intersection of all the predecessor blocks values, out values, and out values will contain the variable name and its constant value, and if they are the same, they will intersect, and like the value will be a constant for this block. And if for some reason they have different values, they won't intersect, so the intersection will be empty set, and the next block won't be able to use this information to change the value of C to the constant.
I'm not going to tell you all the answers. You can work these out and even try them out on real code in your implementation. I do, however, want to give you one example of a backward analysis. We've so far seen fully work through a forward analysis of reaching definitions. Let's think about live variables. And remember, what we're trying to do is calculate the set of variables that have been defined and are going to be used at some point in the future, that is later in the control flow graph. So I've told you that some of the ingredients are that these are going to be sets of variables. Obviously, the domain is sets of variables. The direction will be backward, and the merge function is going to use union. Beyond that, we just need to define the transfer function. And here's my idea. We need to define
the transfer function, of course. I forgot for constant propagation to define a transfer function. If we come into block, we have a set of variables and values, constant values for this variable. We merged already it somehow with intersection. Now the transfer function will be like very much similar to the transfer function we had in reaching definitions. I hope the reaching definitions is the same things that we did previously. So the transfer function will be just overwriting values of the set we get into the inputs. If we have a definition of the variable and its combined out, it will be a bit more trickier. We have inputs. In input we have variable name and if it's a constant or not, and inside the transfer function we need to keep in mind that if our variable depends only on constants provided in the input, it will be also a constant, and it will be in output. And if it accidentally depends on something non-constant in the output, it won't appear. Yeah, I can probably give a bit clearer definition, but just thinking out loud, I guess it's about it's close. My understanding is close to what we should have for the constant propagation. Not sure yet. Probably will be better to check it in practice. But I guess I kinda get it.
this function. We use a little more room here. We need to define this function on, and this goes backward this time. So instead of computing the out value based on the in value, we will compute the in value based on the out value. So for a given basic block, we have an output set of live variables, and we need to compute the input set of live variables, that is the ones that are live at the beginning of the block. So it's going to start with those things that are live at the end. And
okay, reaching definitions, probably something else, because it doesn't have a transfer function here defined, but we already did it in previous minutes of the lecture.
And like before, this is going to have to do with set operations. So we're going to take the symmetric difference to take the things that were live at the end and remove variables that were killed during this basic block, that is like assigned to. So those definitions that you can just write kill B, those are not live at the beginning of the basic block. So it's all the things that were live at the end, except for those ones that we killed somewhere in the middle of the basic block. And then also, there are the uses, that is the things that are defined before they're used somewhere in this basic block. And we'll say that those things are now live. That is, if you refer to X, for example, somewhere in the basic block, and that wasn't live before, well, it's live now. At the top of the basic block. So this data flow equation, this transfer function for live variables, coupled with the rest of the
okay, let's go from the beginning.
And are going to be used at some point in a set of variables of a backward analysis. We've so far seen fully work through a forward analysis of reaching definitions. Let's think about live variables. And remember, what we're trying to do is calculate the set of variables that have been defined and are going to be used at some point in the future, that is later in the control flow graph. So I've told you that some of the ingredients are that these are going to be sets of variables. Obviously, the domain is sets of variables. The direction will be backward, and the merge function is going to use union. Beyond that, we just need to define the transfer function. And here's my idea. We need to define this function. Use a little more room here. We need to define this function on, and this goes backward this time. So instead of computing the out value based on the in value, we will compute the in value based on the out value. So for a given basic block, we have an output set of live variables, and we need to compute the input set of live variables, that is the ones that are live at the beginning of the block. So it's going to start live at the end. And like before, this is going to have to do with set operations. So we're going to take the symmetric difference to take the things that were live at the end and remove variables that were killed during this basic block, that is like assigned to. So those definitions that you can just write kill B, those are not live at the beginning of the basic block. So it's all the things that were live at the end, except for those ones that we killed somewhere in the middle of the basic block. And then also, there are the uses, that is the things that are defined before they're used somewhere in this basic block. And we'll say that those things are now live. That is, if you refer to X, for example, somewhere in the
we are calculating in B, which depends on outputs of the block.
Basic block, and that wasn't live before, well, it's live now at the top of the basic block. So this data flow equation, this transfer function for live variables, coupled with the rest of the ingredients, gives you a global analysis that tells you this very cool information just by plugging it into the existing algorithm. I encourage you to do this for all of them. Take as much time as you want, of course, and just look through all these analyses and try to think through how you would set them up as data flow problems, thinking up the direction and the merge operator and the transfer function. It can be great fun.
Okay, let's make a break. There are optimizations, benefits for tackling both the blocks with both high in out degree and low in out degree, I think. I have encountered lattices from time to time, but I still don't understand them properly. What is lattices? Lattice is like the green leaves. The only thing that I know about lattices. Lattice order. Why I didn't learn like the math in English? It would be so much easier right now, like reading papers or do all this kind of stuff. How it called? in Russian. Okay, okay. Now I see. Lattice Lake. Funny name. I know that lattices are very much in use for static analysis of the program. I'm curious, have I ever met this guy? Probably no. Computing Science PhD. I guess I also need to do a PhD in computer science. I need to learn terminology in English first, I think. What is this cheat sheet? The cool thing about university education, good university education, that you're not freaked out by this PDF when you see it. You're like, it's okay, you need like some time to figure out some parts of it, but overall it's understandable. Looks like a Kotlin inspired stuff backported to Java. Something Arabic here. Family tree. What is this thing? Karate. Java REPL. Looks really nice. Okay. Dun, dun. Oof. What? Where it came from? Oh, it's tooltip. And okay. Okay. In university, I think I wasn't like in love with math, but probably it was because I was overwhelmed with the amount of math we had. Like every semester we had at least a few different type of math, and every type of math required like a lot of effort to pass the exam. I don't even know how I would make it more interesting to learn math in university if I would be in charge of structuring the educational program. From one point of view, you really like need almost all of this knowledge to some extent in your life, like if you go into academia or if you go to some advanced technologies and you really want to understand like programming language theory or maybe some other concepts. But when you are in university, you don't have a clue what to expect in the future, and you are bombarded with all those math concepts, equations like theorems, lemmas, and all that stuff. And if you're not really into like math as on its own, it's really hard to keep being focused on it. It gives you an anxiety and depression, I guess, the amount of math you can like encounter in some strong universities. Okay, I think that we have like a very small video left. Ideally, it would be cool to start doing all those tasks right now and to really implement them to get the experience and to verify the understanding of the concepts that we learn through the lections. But I guess I will do it next week, because next week I will have a bit more spare time, and in addition to that I will be alone and will be able to speak loudly and to start earlier in the morning and work on all that stuff without worrying that I will wake up my friend. And I will be able to be more focused and not distracted during the day as well. So if everything goes well, next week I will spend some time working on the some tasks from the course. Yeah, I think so. Pam. Let's start. Let's start our next round of focus.
right, folks, this video is going to be super short. I just need to introduce you to the programming task associated with lesson 4. It's all about data flow. To put it real simply, your task is basically just to implement a data flow analysis and to convince yourself that it works using tests as usual. So the difference between this and the previous task is that this isn't a transformation on programs. You just have to implement analyses. So for example, you are free to implement any of the analyses that we saw in the previous video that are also listed in the notes associated with this. You can even just implement the real simple reaching definitions analysis that we used in an example. You just have to implement one of them. There's also kind of, if you feel like it, you can feel free to generalize your implementation to a kind of an arbitrary data flow framework that can solve any problem, and to parameterize it so you can feed in several different definitions of data flow analyses. I highly encourage you, however, that in the first phase of your implementation, you just make it work for one. Don't try to overgeneralize as a first step. Just try to make it work once, and then if you have extra time and you're super excited, then you can generalize out from there. It's not that hard once you've done it once, but I really don't recommend trying to get the fully general thing right before you pick a particular data flow analysis you want to run. So for example, I have a few test programs in here. It doesn't really matter what they do, but here's a factorial implementation. I can show off real quick what it looks like to run a simple data flow analysis on this. I need to, as usual, Brill to JSON this thing. And then I will pipe that into my generic data flow solver program, and then it has a few analyses built into it. One simple one is the defined variables analysis. This is just a super simple analysis that it's even more basic than live variables that are guaranteed to be used again in the future. Defined variables just like all the variables that have been written to at some point in the past at this point.
At the beginning of the stream, I was talking that it would be cool to have API for running pipelines inside the Lisp code. And now, right now, I understood that I can probably work around this thing in the following way. I will be generating using gigs a shell files which pipeline a few tools into one program, and I will be just running this program with hard-coded data or maybe some other way, which will eliminate the need for interacting with input and output of the program, and which will allow to bypass the deadlock problem we have. Maybe. Okay, one of the options. Use gigs for a script which contains pipeline and exe from variable, something like this.
And this is the sets of live variables at the beginning and ending of every basic block as labeled in the control flow graph. You are free to use this defined variables thing as kind of a warm-up. I think it's like maybe a little too ambitious for the
Okay, this one doesn't look too hard.
Actual thing that you turn in, a little too unambitious. I hope I said that correctly. But you can do all sorts of other things, like for example, you can find the live variables I've implemented in mine, or I've also done a simple constant propagation analysis for using my data flow framework. And the way that you can interpret this output is that every variable is marked with a question mark. If I don't know what the value is, that is, if it's not a constant, if I can't prove it to be a constant at this point. A little too ambitious for the actual thing that you turn in. You are free to use this defined variables thing, guaranteed to be used again in the future. Defined variables just like all the variables that have been written to at some point in the past at this point. And this is the sets of live variables at the beginning and ending of every basic block as labeled in the control flow graph. You are free to use this defined variables thing as kind of a warm-up. I think it's like maybe a little too ambitious for the actual thing that you turn in, a little too unambitious. I hope I said that correctly. But you can do all sorts of other things, like for example, you can find the live variables I've implemented in mine, or I've also done a simple constant propagation analysis for using my data flow framework. And the way that you can interpret this output is that every variable is marked with a question mark. If I don't know what the value is, that is, if it's not a constant, if I can't prove it to be a constant at this point. And then maybe unsurprisingly, there's a variable called 1 that is guaranteed to hold 1 at every point in the program, and the same thing with a variable called 0. Anyway, go crazy, come up with whatever data flow analysis you want. Just scale it to the time you have available, implement some data flow analysis, and then take it as far as you like. You can implement a fully general framework and 100 different data flow analyses if you really feel like it. I want to show you just one small turnt trick that you can use when you are testing this, which is that, as you might imagine, it might make sense to sort of set up turnt tests so you can validate that, for example, this fact analysis does what I want. If you use the args functionality of turnt, you can see that I've set up the command for my turnt setup to like pass in arbitrary arguments to my data flow analysis. So if you want to run multiple data flow analyses and you also want to do this thing where you like pass the name of the analysis on the command line, you can do that too. And you can specify in the file which data flow analysis you want to use. But turnt also has an args flag. So we're in this like verbose print mode, and we can also say, for example, use the analysis live or defined, for example, on this this program, and then I don't have to remember the whole pipeline every single time, and makes it really easy to run multiple data flow analyses on the same program if you set up your analysis this way. Good luck, and be sure to ask questions in the Zulip thread associated with this lesson.
Okay, let's do one quick thing. CS6120 data flow analysis. Data flow analysis SC. I just want to create a model, and inside this model analysis, and inside this model I will define fn arguments like this. What it gives to me? This gives to me the already starting point that I can use. I will need to have some wrappers from here. Yeah, I think that I will use this namespace to actually do the stuff. What I'm missing in this course, is a bit more structured way to run the tests for the code I write. I understand that there's some turn infrastructure and there's a task use turn with args and all that things, but I would like to be it like even more detailed, like already examples of code snippets that I need to write, and only thing I need to change is a path to my program. Maybe in the repository there's already this kind of thing that I can adjust and get all that stuff. Need to take a look into it in more details. So next week I guess I need to schedule a separate stream for the homework on this lesson 4. So much things to do, not so much time. Oh, 7 concurrent viewers. Where do you come from, my friends? It's a lot of people for watching so boring stuff I'm doing here. Okay, we went through all the necessary stuff to do our homework, and the only thing that is left to actually do this homework I'm sure that I won't do it on my own, because you know, with this course you don't have any external pressure. Like, it's self-guided course. You just go through the lections and like, okay, it's understandable, very clear, very good, very nice, and you just go through the lections and skip all the parts that you don't really understand. And somewhere, I guess, in a couple more lections, you won't just get some stuff, and you will be just, okay, I think I understand the first part, it was easy, I'm not sure if I understand this part, but it will be harder every time to watch the next lection and have a missing pieces. And that is why you need to practice, but without external pressure, without like the necessity to do something. It's really hard to keep to be on track. So I guess I need to schedule a separate stream and do the homework, actually do it. Otherwise, my understanding will be shallow. And in a few more lessons I would like to abandon this course, because I don't like really understand some of the stuff happening. Okay, this was like a meta information about the course and approach of studying. I hope next time on the homework stream we will figure out how to set up the environment for running code and actually executing some tests that we can use to verify that the task we are performing are actually like correctly implemented. I already forgot what those abbreviation means. Local value numbering and DCE. What the fuck is this? Let's get back to schedule. Lesson 3. That code elimination. Of course. Nation. DC is that code elimination. LVN is local value number. Okay. I don't know if I need to rename it to the lesson 1, lesson 2, and so on. Lesson 3, SM. Lesson 4, data flow analysis, SM. But I will figure out it during our homework stream. Okay, it was a very nice stream. We went through the lesson quickly. I was very happy and like active, not depressed, not tired. Very much enjoyed it. I hope you enjoyed it as well. And I hope it was useful for you. I see you in a bit, probably in a few days. Thank you for your time. Bye bye.